So now we're going to talk about the second section, which is different types of causal mediation effects. These are also called different estimands in the literature. So different types of causal mediation effects, different causal estimands. Same thing. We're going to talk about three general types: controlled direct effects, natural direct and indirect effects, and interventional direct and indirect effects. To do that, we're going to start with, I remember that last time we talked about two different DAGs that we would be using, one that did have that Z variable, which was our post-treatment intermediate confounding variable, and then the one that doesn't. So we're going to start, just for simplicity, with the one that does not have that Z variable. So again, we have our baseline covariates W, we have treatment or exposure A, mediators M, and outcome Y. So the first, and I think the simplest type of causal mediation estimand that we can talk about are controlled direct effects. And so this is, writing it using our notation that we talked about last time, right? It's like that notation is so important. So I'm writing it using this notation here, right? And so it's the difference, the average expected difference of our counterfactual outcome had treatment been set to 1 versus had treatment been set to 0. And in both parts of the contrast, setting the mediator to one particular value, little m. And so you could think about, okay, every person in this population is having their mediator value or values set to one particular value, little m. So again, we see that here, and it is set uniformly for everybody in the population or in the sample that we're taking this effect over. So again, this effect is comparing treatment on versus treatment off, treatment value 1 versus treatment value 0, and undersetting some constant value of the mediator. Okay, so now we talked about this causal mediation estimand. Our next step is to understand, well, under what assumptions do we have to make for us to be able to actually write this causal estimand as a function of the observed data that we actually have? Because remember, in real life, we don't have these counterfactual values. These are like hypothetical values. We don't see them, we don't have them. And so we have to make assumptions in order for this causal estimand to actually be a function of data that we do have in real life. So what assumptions are those? And so these are also called identification assumptions. They're assumptions that when you hear it, you'll be like, oh yeah, like I've heard of no unobserved confounding before. And what that means is these are the assumptions we have to make in order to give us license to actually move forward with this type of effect in our data analysis. Okay, so for the control direct effect, we have to say that we're assuming there's no unobserved confounding of this AY relationship. And so what that means is that W, the variables that we've included in our W, represent all the confounders of the relationship between A and Y. Now, going back to our hypothetical example, if A is randomization to medication 1 versus medication 0, then we're okay with that assumption, right? Because there shouldn't be unobserved confounders because we randomized A. Our second unobserved confounding assumption for control direct effects is that there's no unobserved confounders of the MY relationship. And so what that means is that, as long as we have all our confounders, again, measured in W, then we don't have a problem. Then we can meet that assumption. Now, for a lot of mediation, I actually think that this assumption here is probably, the hardest for control direct effects because, typically the mediator value isn't randomized. So where it's like we're in an observational study and we really need to make sure that we're measuring all possible confounders of this mediator outcome relationship. Okay. We also have positivity assumptions, which I'm not going to talk about so much here, but they're here, to help all of you whenever you're doing your mediation analysis and writing it up. So again, for control direct effects, we would just need to assume that, I'm going to actually start with this bottom assumption here. We would need to assume um, that basically there is a reasonable probability of getting each value of the treatment of interest for every strata of covariates. And then for the mediation, for this top bullet, we would need to assume that there's a reasonable probability of getting the particular mediator value that we're setting to everybody. There's a reasonable probability of getting that for every strata of covariates and for each of our treatment values that we're interested in contrasting. Under these assumptions, we can do what's called identify the control direct effect. So this is just the rewriting of our causal mediation estimand as a function of observed data. And so you can see that here, that here's our counterfactual outcomes, right? But which we don't see. But you can see on this right-hand side, well, these are all random variables and we have these in our data. And so this is again saying like, we want to be able to interpret this as causal. But what we have is, not counterfactuals. So what we have is this, and under the above assumptions, we have license to interpret what's on the right-hand side as what's on the left-hand side. Okay, so I'm just going to walk through this really quick. And so on the right-hand side, we have the expected outcome, just like our regression, right? Our expected outcome conditional on the past, but contrasting setting A equals 1 versus A equals 0, and having M set to some specified value, little m, for everybody. And then this outer expectation, that's just taking the overall average. So we have these conditional inner expectations. When we take the overall average across them, it's like we're marginalizing across all of our baseline covariate values. We're going to build, if that didn't make a lot of sense, don't worry about it. Just taking the mean, right? We can just take the mean. So we have these expected values and we're taking the mean, but to build more intuition, I'm going to show the toy example R code again. So again, we have our simulated data just like before, where we're simulating our baseline covariate, our treatment, our mediator, and our outcome. First, we're going to fit a correct model for our outcome. So just a linear regression of Y on M, A, and W. You can see that this looks a lot like this up here, right? And now we're going to assume that we want to estimate the control direct effect, setting everybody's mediator value equal to 0. So that's what this is saying. And then we're going to generate these predictions. So we're going to generate this green part here. So we're going to use the predict argument function in R. So we're going to predict from this linear model that we fit under a copy of our data. So that's this part. We're just copying our data, but we're setting A equals to 1, M equals to 0 in one data set, getting these predictions. That's this green component up here. Second, we're setting A equals to 0, M equals to 0, generating those predictions. And that's this green component up here. So now we actually have the ingredients we need to actually estimate the control direct effect. So we're just going to take the difference between those two predictions, which is this inner part, and we're just going to take the mean of the whole thing. And that's all that outer expectation is. When we do that, we get that the control direct effect is estimated to be 1, which is what we want. So we can then ask ourselves, so that's what is the control direct effect? How do we do it? We also need to think about number 3, is this the actual causal mediation estimand that we want? It makes the most sense if we can intervene directly on M. And I think, in thinking through, well, can I intervene directly on M? So if we can think about if there exists a policy or a hypothetical policy that would set everybody to a single constant value of M, I think that that's pretty hard. Pearl calls this a prescriptive type of estimand, because we're literally prescribing what everybody's value of the mediator has to be. An example that I came up with a while ago is, let's think about air pollution as the exposure. And then you could envision setting like some sample of people, everybody to a constant rescue inhaler dosage as their mediator. And then you could look at hospital visits, for example. A negative about this type of mediation estimand is that it doesn't actually provide a decomposition of the average treatment effect, or this like total effect, right, of A on Y into a direct component and an indirect component. We're only estimating the direct component. And so what if our research question doesn't involve intervening directly on the mediator, or what if we want to decompose the average treatment effect, or the effect of A on Y again, into its direct and indirect counterparts. So if we want to do either of those two things, then the control direct effect is not for us. And so then we might want to move on and think about natural, direct, and indirect effects. So we're going to use this same DAG as above. So again, we're using this DAG, which is the one without Z variable in it. And then we're going to remember from the last section our definition of a nested counterfactual, right? And again, this is interpreted as the outcome for an individual in a hypothetical world where we gave treatment, but the mediator was whatever value it would have taken for that individual under no treatment. And when we're doing these contrasts, when we're thinking about natural, direct, and indirect effects, these are contrasts of a nested counterfactual. And so here we're thinking about contrasting, for example, somebody's mediator value under treatment versus their mediator value under no treatment. So remember before, for the control direct effect, everybody had the same mediator value, right? It was held constant for everybody. For these, we're going to think about a hypothetical counterfactual mediator value under treatment, and then a potentially different hypothetical counterfactual mediator value under no treatment. We're also going to make use of this fact that because of the definition of counterfactuals, this nested counterfactual y sub a equals 1, m under a equals 1 is the same as, is equal to y sub a equals 1, or y under a equals 1. That allows us to decompose the average treatment effect, or this total effect of A on Y, which we can write like this. It allows us to decompose that in this way. So here we're just rewriting this average treatment effect, or ATE, just making use of this above fact. And then we can show with some algebra that it equals the natural indirect effect, which is this component. So A equals 1 for both parts of this contrast, but contrasting these two counterfactual mediator values under A equals 1 versus A equals 0. And then the natural direct effect, which is holding the mediator constant at whatever value it would have taken under no treatment, and contrasting A equals 1 and A equals 0. So I said this in words already, but if you want, it is in words right here. Again, these are counterfactuals. And so we again have to think about, okay, we might want this interpretation of causal, but we don't have these counterfactual variables. We only have our observed variables. So what assumptions do we need to make to interpret the quantity that we can estimate as causal, as these natural, direct, and indirect effects? Now, the identification assumptions for the natural, direct, and indirect effects are the hardest, and I think they're really the hardest to satisfy. So these first two are the same as what we had for the control direct effects. So no unobserved confounding of the treatment and outcome relationship, same as what we had last time. Second bullet, no unobserved confounding of the mediator outcome relationship, same as last time. The third bullet is another no unobserved confounding assumption, but now it's no unobserved confounding of the treatment mediator relationship. So different from last time, that's one additional one. That one may not actually be that much harder to satisfy, right? Because if we don't have unobserved confounding of the treatment outcome relationship, maybe it's also pretty likely that we don't have unobserved confounding of the treatment mediator relationship. This fourth one, though, is a real doozy. And I think this is why, I think a lot of cases, natural direct and indirect effects aren't actually appropriate for a lot of our questions. This one is hard to think about. What you'll notice with this fourth assumption is that the mediator, it's making an assumption about the counterfactual mediator in one world, had we set treatment equal to the reference value, and how it's related to the counterfactual outcome under the opposite hypothetical world. So it's relating these two counterfactual variables, but in two hypothetical different worlds at the same time, under treatment and under no treatment. This is called the cross-world independence assumption. So what does it mean? So it means that conditional on these baseline covariates, the knowledge of the mediator value in the absence of treatment, which is this, can provide no information about the outcome under treatment. It's this part. The issue here is that this assumption is violated whenever we have such a Z variable that we had in the previous DAG. So if we have a variable that's affected by our treatment and goes on to confound the mediator outcome relationship, we violated this assumption. This, if you think about, particular research questions you might have about mediation, this is almost always violated. You can almost always come up with example of variables that you have that violate this assumption. So for example, adherence. So if we think that treatment assignment works through whether you started taking the treatment, whether you adhere to the treatment, and those are not your mediators of interest, now you're violating that assumption. These cross-world assumptions are problematic for other reasons, including that we can never actually design a randomized study where the assumption holds by design. And that just means that, typically we think about causal inference and we think about, well, how would we test this? Is there a experiment that we could design that would give us this answer? And in this case, again, because it's about two different worlds at the same time, there's no experiment where we can both assign somebody to treatment and the exact same person at the exact same time is also assigned not to treatment. Now, if this assumption holds, though, then what we can do is we can write the natural direct effect as a weighted average of the control direct effects at each level, setting m equal to m. And so this is a link, then this provides a link between control direct effects and natural direct effects. In addition, because this is this averaging across these levels of m, you may also be intuiting that, oh gosh, okay, actually, if my control direct effect is constant, no matter what value of my mediator I set, then the control direct effect is actually equal to the natural direct effect. And it is in this case where, back we talked about Barron and Kenny, like the most popular method. Like if you're in this case, then you can interpret the Barron and Kenny approach, and you have correct model specification. You can interpret that as a causal effect in that very special case. Okay, so under the above identification assumptions, the natural direct effect can be identified as this. And so you can see that this green part, it looks the exact same as we had the control direct effect before. Now we're just taking the average. Now we're taking, one set of averaging, but setting A equal to 0, taking that average, and that's going to be an average right across M. And then we're taking one more average. So again, this is for the natural direct effect. We can identify the natural indirect effect similarly. And to build further intuition, we can do this in R. So we're just generating our same simulated data as we did above, fitting our correct model. We're getting these green predictions exact same as we did for the control direct effect. So I won't go through this. All of this is the same. We're getting our predicted values. We're taking the difference. Now we're going to use this difference as an outcome for a subsequent regression. We can call that a pseudo outcome. So we take this difference, we're going to name it pseudo. We're just going to do an additional regression, which is right here, where we regress it on A and W. Now we're going to generate predictions from that regression, setting A equal to 0. So we have our new data frame where we're setting A equal to 0. We're generating predictions from that, pred pseudo, and we're taking our final outer expectation, which is just a mean. So we're taking that very last mean. Here we go. And we're getting an estimate of very close to 1. So this looks very similar to what we had before. We're still estimating that this direct effect is equal to 1. So in this case, the direct effect looks essentially the same as the natural direct effect looks to be essentially equal to the control direct effect. So again, this is what are natural direct and indirect effects? How do we estimate, what's going on behind the scenes? What do we have to assume to estimate natural direct and indirect effects? But we also need to think about, is this the estimand that I want? And I think maybe, if it makes sense to intervene on A, but not directly on M, so if we're in a scenario where the controlled direct effect doesn't make sense because we can't in real life intervene directly on M, this could be appropriate. And we want to understand this mechanism, this natural mechanism that's underlying this total effect. Pearl calls this a descriptive type of estimand. Another advantage of natural direct and indirect effects is that they add up to the total effect. So you do actually get this decomposition where, okay, I had this total effect of A on Y, and I'm decomposing it into the portion that operates through M, which is the indirect effect, and the proportion that doesn't operate through M. The issue is that we have to be okay with these assumptions, like in particular, that fourth assumption, which I think is really problematic frequently. So next we're going to talk about, well, what if our data structure involves a post-treatment confounder of the mediator outcome relationship? So we're going to be talking about what if we're actually not in the DAG that I was showing above, but we're actually in the DAG that contains this Z variable. Okay, so now we'll pick up where we left off last time, and we'll talk about our last type of path-specific causal mediation estimand, which are interventional, indirect, and direct effects. So remember last time we talked about natural, direct, and indirect effects. So I'm going to go back there for a second, which thinks about, for the indirect effect portion, contrasts two potential mediator values for the same person. One where their mediator is whatever it would have been had treatment been set to some value, let's say little a, versus whatever that individual's specific mediator would have been had treatment been set to a different value. So let's say A star. Interventional direct and indirect effects are a little different. So we're going to notate them about, similarly, but we're going to use this G instead of M. And that G is on purpose because what that's going to be is instead of being the counterfactual mediator value for somebody, it's going to be a random draw from a distribution of counterfactual mediator values for that person. So it's like kind of hard to think about, but I have a picture here so you can think about, for example, a distribution of mediator values conditional on covariance W under some treatment assigned treatment equals little a versus a different distribution of mediator values, again, conditional on covariance under treatment something else, little a star. And so this GA is going to be, okay, what if we draw from this distribution, had treatment been set to A, G little a star would be what if we had drawn from this alternative distribution of mediator values, had treatment been set to A star. Okay, so that's this first part. So now we're just going to follow that all the way through with our counterfactual. So we're going to define the counterfactual outcome, Y under A equals 1, G sub 0 is the counterfactual outcome in a hypothetical world where treatment is set to value 1 and our mediator is set to this value G0, which is really a draw from this distribution of counterfactual mediator values had treatment been set to the opposite, which is 0. Then we can define y sub 0, g0, and y sub 1, g1 similarly. Using those three counterfactual outcomes now, we can do a slightly different decomposition where we're showing a different total effect decomposed into the interventional indirect effect. So you'll see that this really looks very similar to the natural indirect effect, only again, what was before contrast of M sub 1 versus M sub 0 is now a contrast of G sub 1, G sub 0. And the interventional direct effect, which again, you'll see again looks very similar to the natural direct effect, only instead of having this M sub 0 for the red part, we have G sub 0. I do want to talk for a minute about what's on the left-hand side of this equation, which is note that this is still a total effect of treatment. If we do have the presence of those intermediate confounding variables Z in our DAG, we expect it to be slightly different, or it could be a lot different. We expect it to be different from the average treatment effect. That is this. And so that is a downside of these types of effects. So what we do, why would we use these types of effects? I think we would use them, again, if we have the presence of one or more important intermediate confounding variables that would fall into that Z bucket. We're going to gain the ability to solve a problem, but we're going to, there's no free lunch. So there are some trade-offs here. So we're going to lose in terms of interpretation of the causal effect because we're not decomposing this average treatment effect. We're composing what we think is a slightly different total effect. Okay, so just to say a little bit more about this, so above we define this G sub A as this random draw from our counterfactual distribution of mediator values conditional on W. Now, what if we instead define G sub A as a random draw from the distribution counterfactual mediator values conditional on this intermediate confounding variable under A and W? So it turns out that if we do start conditioning on this Z variable, then the indirect effect defined in this way, we're actually only measuring the path then A to M to Y and not the path A to Z to M to Y. And so there could be important reasons to choose one over another. So we won't get into this, but you can look at this and you can look at the references on this page if you want more details. But just to say, there's additional nuances with this that we won't, we're not going to get into for the sake of time. Okay, so for these effects, we've done away with that problematic fourth identification assumption that we needed to have for natural direct and indirect effects. And so what are we left with? We're just actually left with the standard sequential exchangeability or sequential randomization assumptions, where we are assuming that we don't have any unobserved confounders of the A to Y relationship, the treatment to outcome relationship. We're assuming we have no unobserved confounders of the mediator outcome relationship. And we're also assuming no unobserved confounders of the treatment to mediator relationship, as well as positivity assumptions. So again, the reason to do this, to use these types of effects, are to get rid of that fourth very problematic identification assumptions, which is needed if we do have these intermediate confounding variables. So under these above assumptions, we can define then the interventional direct and indirect effects like this. So you'll notice here, I have just one component of the causal contrast. And, we just need to show identification of one of those components, right? Because we have a contrast of two components, and so the other one follows. So it looks, again, we're kind of starting out the same as what we have been doing in this green. This green component is just our regression, our outcome model regression. And then we're going to marginalize over our intermediate confounding variables, Z. And then lastly, we'll marginalize over our mediator variables that we have here. That's this purple step, and then we'll take the mean at the end. So same as what we've done before, we're just going to go through our code, just step through it, build some additional intuition. We have our same simulated data here as before. what we're going to do is we're going to compute this particular component of the contrast where we're saying we're going to set treatment equal to 1. And we're going to draw our mediator from its counterfactual distribution had treatment been set to 0. Okay, so again, we're starting same as before. We're just fitting a regression of our outcome model, which I'm showing here. And we're generating predicted values under this A equals 1 to get this part. We're also generating predicted values under both all the values that Z can take because we are going to marginalize over Z. So in order to do that, what we have to do in this case, what we fit up here, Z can only take 2 values, 0, 1. We did that for simplicity. So we're going to get our predicted values out for our outcome regression under setting A equals to 1, and then Z to each of the values it can take, 0 and 1. Okay, so now we're fitting our model for Z, and that's just a function of A. We get and you can see that up here, right? So this is just our true model, Z as a function of A, and we're going to get the predictions from that model, again, under A equals 1. We get this prediction, and now we can do this marginalizing out of Z. So again, because we only generated Z with 2 values, this is actually pretty straightforward. So we can just take our predicted value of our outcome under Z equals 0 times the probability that Z equals 0 plus our predicted outcome under Z equals 1 times the probability that Z equals 1. Now we can regress that pseudo outcome again on A and W, and we're going to compute prediction setting A equals to 0, and that's going to function as marginalizing out our mediator. So we get that here. So we're setting, here's our regression of our pseudo outcome on A and W, and then in this line, we're generating those predictions setting A equals to 0. And then lastly, we just take that mean again, and what we estimate is this component being 1.2 about. And so again, we're going to do the exact same thing in order to get those causal contrasts of the interventional indirect effect and direct effect. We're going to do the same procedure for setting A equal to 1 and then setting that draw from the mediator under A equals 1, and same thing setting A equal to 0, drawing from the mediator under A equals to 0 to obtain this decomposition. Okay, we do want to ask ourselves now that we know, again, like what are these effects and, what are these effects? What are they identified? What assumptions do we need for identification? We now need to ask ourselves, is this the estimand that I want? So, it might make sense for you if it makes sense, theoretically at least, to intervene on that treatment or exposure variable A, but not directly on your mediator variable or variables. Again, if we want to understand a descriptive type of mediation, we have to be okay with the assumptions as well. I do want to talk about, though, a really important limitation of interventional effects. Caleb Miles recently talked about this in this paper, which you can, click on and read if you're interested. And what he said is that he defined something that he calls the sharp mediational null hypothesis, which we don't really need to get into, but we can talk about what the problem is. And so the problem that he uncovered is that there can be actually no people in your data, in your population, there can be no one individual who has their treatment affect their mediator, which then goes on to affect their outcome. So if we're walking through this, that means that no individual in the entire population has this indirect effect. But it could be that your interventional indirect effect is actually non-zero. Whereas I just told you that no individual has that mediational pathway. So we would expect that we would estimate a 0 indirect effect, a null indirect effect. Interventional effects, because we're drawing them from these distributions, these mediators, it can be non-zero in the case if we have one subset of the population that has a relationship between the treatment and the mediator, and we have a totally distinct subset of the population that has a relationship between the mediator and the outcome. in that particular case, then we can have an interventional indirect effect that's non-zero, even though there is no one person in the population whose effect of A on Y is mediated by M. Is this an important problem in practice? I don't know. My personal opinion is no, just because we have to be in this particular, what I could think of as kind of this edge case where we have to have these two distinct subsets of the population, and I don't know how often that would happen. Okay, so one other thing to think about for these interventional direct and indirect effects is that let's say that this Z variable, this intermediate confounder variable, does not exist. In that case, then our interventional direct and indirect effects should match up with our natural direct and indirect effect estimates. Okay, so we talked about a lot. I'm including this table that's just a summary from a 2019 paper that just basically reviews what we talked about. So control direct effects, natural direct and indirect effects, interventional direct and indirect effects. It, gives those of estimands using our counterfactual notation that we reviewed in this first module. It gives their descriptions in words. And then it gives the identification assumptions that we need in order to identify these effects in addition to positivity and consistency.